In this video I want to give you a recipe for constructing a huge class of spaces called CW complexes or cell complexes, and these are really the spaces that we tend to think of in topology. So almost all the spaces we care about are at least homotopy equivalent to cell complexes. So in order to understand this video, you're going to need to know about the quotient topology, so you should watch the video introducing the quotient topology before continuing. A CW complex is a space built out of smaller spaces iteratively by a process of attaching cells. A cell means a disk of some dimension, so I'm going to write dk for the disk of radius 1 in Euclidean k-dimensional space. So in other words, it's the set of vectors x in Rk such that the length of x is 1. This is the disk. And when I say attaching it, I mean maybe we've built some space x and we want to glue a disk to x in such a way that its boundary sticks to x and the rest of the disk sticks out of x. So this is attaching a cell. And if it's a k-dimensional disk we're attaching, we call this a k-cell. So for example, you might start with x being just a single point, and you might attach a one cell, in other words an interval. Right, this is the one-dimensional disk, it's just an interval. And you could attach it so that its two endpoints both mapped to this point in x. Maybe I'll do it in red. So this is the one cell. And you can see you get a circle. Similarly, you could have started with a point and attached a two cell. So that its boundary, maybe k equals 2. Two cell looks like this. Its boundary is going to map down to this point. Every point on this circular boundary is going to map down to this single point here, and you get a sphere. You could attach several cells. So let's again start with a point. We could attach a one cell here and another one cell here. We get the figure 8 space. The torus, for example, that's another cell complex. Let me draw it like this. So we've already seen that if you identify the opposite edges of a square, you get a torus, and inside that torus you can see these two circles, which you get by just looking at these edges. So maybe one of them will look like that and one of them will look like that. And the point is now, if you think of this, maybe I'll do it in red, as x, right, which is the space we built in the previous example, a wedge of two circles, then the torus is obtained from x by adding a square. And what is a square? Well, topologically it's the two disk. So this is a two cell. Right, the fact it's got corners doesn't stop it from being homeomorphic to a two-dimensional disk. So you can see the torus, the two-dimensional torus, is built up by attaching a two cell to the figure 8. The boundary of that two cell winds around the two factors of the two circles in the figure 8 in this way. It kind of goes along the first one, let's say A, then along the second one, B, and then backwards along A, and backwards along B. And that tells us how exactly we should attach this 2-cell to the figure 8. So you can see many of our favourite spaces are built up from the simplest spaces, like points, by attaching cells iteratively of higher and higher dimension. That's what a cell complex is. Let me give you the rigorous definition of what it means to attach a cell and what a CW complex is. So attaching a cell, let's say a K cell. I take a space X to which I want to attach this cell. I add the cell just as a disjoint union. So here's X, here's the cell. And now I need to specify some way of attaching the boundary of the cell to X. Right, I need to glue it on somehow. So what I need is a map. I'm given a continuous map from the boundary of the K cell to X. Let's call it phi. We define an equivalence relation. Tilde, which is going to send, or it's going to identify a point, say Z in the boundary of the disk, with its image under this map. And then we define the space that we obtain by attaching a K cell to just be the quotient of this disjoint union by this equivalence relation. So this is why I said you need to know what the quotient topology means in order to equip this with a topology. Now, that's what it means to attach a k-dimensional cell to a space, and this continuous map phi is actually a really important part of this definition. So for example, just looking at this example of the torus, let's suppose I took the figure 8 and I attached a 2-cell instead using the constant map. So here's my 2-cell. Let's suppose I just attach all of the points in the boundary to this cross point of the figure 8. So this is often written as X union phi dk. In this example, it's d2. Right, so if I glue all the points in the boundary to that single point, what I end up with is a circle, and a sphere, all wedged together at a single point. And that's not even homotopy equivalent to the torus. Right, the torus, when we compute its fundamental group, we actually get z squared. That's abelian, whereas here the fundamental group will turn out to be z star z, non-abelian. So different attaching maps give completely different, in general, completely different spaces. Right, because the attaching map for the 2 torus was this one where the boundary went A, B, A inverse, B inverse, whichever way that is. As an even more extreme example, let's just take a pair of points and let's attach a 1-cell in 2 different ways. So you could imagine the boundary of the 1-cell is a pair of points, so we need a map from 2 points to 2 points. So if that's maybe the identity map, we'd get this, right? We're just gluing this boundary to this point and this boundary to this point. Whereas if I were the constant map, sending both the boundary points to this one, we'd end up with a circle and a point. So this is 2 points union along some attaching map phi 0 with a 1 cell. Well, this is sending, so this is phi 0 sending 2 points to 2 points via the identity map. Whereas this one over here is 2 points union a 1 cell along some attaching map phi 1, and phi 1 goes from 2 points to the boundary of the 1 cell to 2 points via a constant map. Right, you can see in this case you get the interval, in this case you get a circle and a point, so they're not homotopy equivalent because this one's disconnected, for example. Okay, so I want to now define what a CW complex is. A CW complex is any topological space built using the following rules in the following way. You start off with the empty set, and then you start attaching 0 cells. So a 0 cell is just a point, right? It's the 0-dimensional disk. So you start with the empty set, you add as many 0 cells as you like, and you get some discrete space, just a bunch of points. Could be infinitely many. And then you add a bunch of 1 cells. Again, it could be infinitely many. And you get some space like this. And you could have like a wedge of infinitely many circles. That's fine. And then you add to this 2 cells. So maybe I should give this a name. So this guy with just the 0 cells I'm going to call x0. This with just the 1 cells I'm going to call x1. You add 2 cells. Of course, you have to specify what the attaching maps are at each stage. And you end up with some space that I'm going to call x2. Dot dot dot. Which means I continue in this manner, forming spaces x0, x1, x2, x3, etc. And these spaces are called the skeleton. So this is the 0 skeleton. This is the 1 skeleton. This is the 2 skeleton. And at each skeleton, at each point, you're attaching your n-dimensional cells to the n-1 dimensional skeleton. So you only attach 1 cells to the 0 skeleton, you only attach 2 cells to the 1 skeleton, etc. I mean, it could be that you don't attach any 1 cells, in which case x1 equals x0, that's possible. And so you obtain a sequence of spaces, x0 inside x1, inside x2, dot dot dot, and you kind of want to make sense of x infinity. And then there's a slightly delicate thing you need to do. So we let x be the union over all k bigger than or equal to 0 of xk. Well, we understand that x1 sits inside x2, so this union is really like taking the limit. of this sequence of inclusions. Technically, this is known as the direct limit. And what that means is I take this as just a set, and then I equip it with a topology and the open sets in this topology are precisely the subsets U such that U intersect xk is open for all k. So this is just a technical thing. I mean, it's really important when you're looking at these sort of infinite cell complexes. We're not really going to be looking at them so much in this course, but they're really there. They're very important objects in topology, so it's kind of important you've seen this definition. And roughly speaking, it just means if you want to talk about open sets in an infinite dimensional space, they're going to be the sets where each intersection with a finite dimensional subset is an open set. So where you have this exhausting sequence of finite dimensional spaces that you use to build up your infinite dimensional space. So this is what's called the weak topology. On X. It's not the same as weak topology. If you've seen it in a course on function analysis, it's something else. And so this is only really important for infinite dimensional cell complexes. And the W in CW stands for weak. So this is responsible for the W in CW. So in another video I'll talk about what the C stands for, and the W is the weak topology. But I'll often just talk about cell complexes because these kind of issues are not really going to concern us in this course. So I just want to finish with a couple more examples. I said you could build up a circle by attaching a one cell to a point. You can also do it by attaching two one cells to 2 points. There are many cell structures on the same topological space. You can do the 2 sphere by either attaching a 2 cell to a single point or by attaching two 2 cells to the circle. Right, so you build a circle up by taking 2 points, attaching 2 1 cells, and then you attach a northern hemisphere and a southern hemisphere to get the 2 sphere. Similarly, S3 has a northern hemisphere and a southern hemisphere that's separated by a 2 sphere. So I don't know how to draw this, but you could imagine drawing it like this. So this is an S2 equator. This is a 3 cell called the northern hemisphere, and this is another 3 cell. Dot dot dot, and you can keep adding pairs of hemispheres to get higher and higher dimensional spheres, and so you can either stop at some point and you have the n dimensional sphere, or you can keep going and you get the infinite dimensional sphere, which you can equip with the weak topology. So that's just an example of the kind of thing you can construct with this sort of infinite construction. So in the next video we're going to see something called the homotopy extension principle, which applies in particular to cell complexes, and that's going to allow us to do things like the following, to argue that if you have a cell complex like this one, where I've got 2 0 cells and 3 1 cells attached in this way to get a theta graph, I could maybe contract this central 1 cell to obtain another space which has just got 1 0 cell and 2 1 cells, and this is a homotopy equivalence. So it kind of looks obvious and it's going to follow from the stuff we do in the next video on the homotopy extension principle, and that really, works very nicely for CW complexes, which is why it's such a nice class of spaces.